playing. Are you all right? Okay. Ah, wonderful. Okay, so good afternoon, everyone. Welcome to this edition of the NITheCS. My name is Francesco Petruccione, for those of you that don't know me. And this afternoon, I have a really big, huge pleasure of introducing to you Dr. Yaseera Ismail. Yaseera just co-published a very important paper in Nature last week. Yeah? And I'm one of the minor contributors to that paper as well. Yeah, but it's the fruit of a very long story that started probably back in 2007 when in Durban, well, both of us were in Durban. Maybe Yaseera joined a little bit later.
Yeah.
We started doing quantum communication experiments, yeah, that nobody was doing in South Africa at the time. Yeah? And a few years later, we were very famous because for a short while, because during the FIFA World Cup, we conducted a quantum key distribution experiment securing the link between the FIFA stadium in Durban and some risk management center somewhere in the city. Yeah? And it worked because otherwise nobody would have seen the soccer matches in Durban at the time. Yeah? And since then, because we, as Yaseera will tell you just now, quantum communication in fiber works only for a couple of 100 kilometers. The only way to reach further distances is to go via satellite. Yeah? And since that time, we're starting, and there is some, is it my laptop that creates this problem? I don't know. No, it's not my laptop. I don't know. Anyway, we started lobbying for satellite connections. Is it your laptop, Yaseera?
No.
Okay, I don't know. Okay, we found a culprit. Yeah. Anyway, so we've been preparing this for a long time, and eventually last year we did a famous experiment that Yaseera will tell you everything about. Yeah? But I forgot to introduce Yaseera. Yeah? So Yaseera is a senior lecturer in the Department of Physics here in Stellenbosch, and she was at some stage my PhD student and my postdoc. Yeah, and now she's way more famous than me. She's also the vice president of the International Commission for Optics, yeah, and she's a, a fellow of the South African Young Academy of Sciences. Yeah. So Yaseera, it's really a pleasure to have you here speak about this nice experiment, and everybody here is keen to hear what you have to say. Thank you very much, Yaseera.
Thank you, Francesco. So just to add to what Francesco said, you know, we've been waiting in anticipation since October last year to share this groundbreaking results with you. We were asked not to share any information until the paper was published. And so we were waiting, and last week, 19th of March, the paper went live at 6 p.m. South African Standard Time. And now we get to share this remarkable experiment with you. So, you know, just to put into context, if you have not seen the buzz going around, but I'm sure most of you have, the reason why this is so important is this is the first quantum satellite link on the Southern Hemisphere. It's also the longest intercontinental link of 12,900 kilometers that has been established between China and South Africa. Furthermore, it's the first quantum satellite link between the Northern and the Southern Hemisphere. And we in South Africa, in Stellenbosch University, obtained the highest secure key with the microsatellite Jinan-1. So it hit many milestones, it has many breakthroughs, and so we are quite happy to be involved in this multi-institution collaboration. So you can think research of this nature is not just a few institutions, it was numerous institutions in China and then Stellenbosch in South Africa. So I'm quite happy to share this most recent results with you. Okay, so just to put this into perspective, we come at a time to share these results when, or this groundbreaking research when this year we all know is the International Year of Quantum Science and Technology. And UNESCO declared this year the International Year of Quantum Science and Technology due to theoretical breakthroughs that was demonstrated in 1925. And the whole aim of the year of 2025 is to promote and help raise awareness of quantum science and quantum technology to the public and look at applications of quantum science in all aspects of life. And so this is kind of pride moment for us, quite a pride moment for us as well, to say that we can share this groundbreaking results in this year of the International Year of Quantum Science and Technology, where we can promote the longest intercontinental link established. Now, the opening ceremony of the International Year of Quantum Science and Technology took place at the UNESCO headquarters in Paris on the 4th and 5th of February. And it was an honor for me because I was invited to be one of the invited speakers at the event to represent South Africa. But the reason I share this anecdote with you is not because the privilege of not only being on the stage of UNESCO. It was, I think, 30 minutes before I could get onto stage, we received the news that our paper got accepted for publication in Nature. And that is why I share this anecdote with you. It was so overwhelming for me to know that the paper was accepted, and there I am going to take the stage at UNESCO to basically discuss quantum research and quantum technology on the African continent, knowing that this paper was just accepted. So that's why I share this anecdote with you. I've been wanting to share this anecdote with many of people, but now I've only shared it with Francesco. So now we can let the news fly. So, as you know, on the 19th of March, this paper was published online, and you can see it's quite a number of researchers from China at the different institutes, and then Francesco and myself in Stellenbosch University. And what I should mention, and I think it's been blocked up at the moment, is that this paper has already hit almost 2,883 accessed already. So it was just published and has been accessed widely. And we all know that this will probably be the most cited publication for a very long time because of this groundbreaking results. I would also say, besides actually having a publication in Nature, Francesco and I would also agree that one of our milestone achievements is being a co-author with Professor J.W. Pan at the University of Science and Technology of China. And the reason why is he's leading quantum technology in the world, specifically quantum communication. He is the leading researcher of quantum communication in the world. Okay, so since the news has been shown to everyone. We've seen numerous headlines. South Africa and China breaks 12,900 kilometer ultra secure quantum satellite link. And I'm sure you've seen these pictures already, but these are the sites, or this is the site in Stellenbosch. So where the ground station was based, it was based on top of the engineering building here at Stellenbosch University. And I'll explain why we specifically picked that point to mount the ground station, and the reason why that area was so prime for these particular experiments. So just to give you a little bit about what's going on, a lot of media picked up this groundbreaking results. You can see Phys.org released and Nature immediately released an article about the groundbreaking research. You can see some of the titles: world's first quantum microsatellite, very important, and I'll explain why. Mini satellite paves the way to quantum messaging on Earth. So there's a lot of development of nice groundbreaking results that came out of this research. It was picked up as far as Sri Lanka. So Sri Lanka picked up this, so it came into the Sri Lanka Guardian. It was picked up in the Citizen in Korea. Business Korea followed the news. So it really has been picked up on numerous different titles throughout. Quantum satellite sets global spanning distance record. So it has really hit the news. Apart from that, it's also been picked up in many places locally. So News 24 followed the story, Mail and Guardian as well. So it's already been hitting the news. And so this ultra-secure quantum satellite link seems to be the technology of the future. And I should mention it also topped Bilibili. So Bilibili is the Chinese version of YouTube. And one of my collaborators on WeChat sent me a message saying in Chinese, so I couldn't understand it, but that it topped the world groundbreaking results for the year, Bilibili's quantum satellite between South Africa and China. So it really has made its rounds. So that was just to give you some understanding of where the media. We'll now get into the actual science. So if we look at the applications of quantum technology, we know that these three areas, quantum computing, quantum communication, and quantum sensing. I'm specifically focusing on quantum communication, which looks at long-term protection of information. And the reason this field is so important is if we have a universal quantum computer, then current encryption techniques becomes obsolete. And so we need an alternative method of encrypting information. And the alternative method is using quantum communication because of the fact that you can't break the laws of physics, you can't really break a quantum system. And if you do try to leave traces in a quantum system, those traces can be detected. So just to give people a perspective of what is communication and what I mean by encryption, I'll just go through this briefly. If we look at current methods of encrypting information classically, we know we take a message, we have to encrypt it using some encryption algorithm, which is a mathematical construct, normally the inability to factorize a very large number. And this creates a ciphertext, which is uh, unreadable to anyone that doesn't have the decryption key. And only if you have the decryption algorithm or the decryption key, you can actually obtain the plain text again. However, one of the faults of this algorithms is that if you have very powerful resources, you can brute force attack and break some of these algorithms. So these are now a little bit far back, but you have seen that over the years when these protocols are invented, they can be broken. And a universal quantum computer can break some of the current encryption techniques that we use, like RSA, elliptical cryptography, as well as Diffie-Hellman. So we have to now look at alternative ways to secure information, but we can't wait for a universal fault-tolerant quantum computer to start learning how to protect information. We need to protect information now and keep it secure so that once a fault-tolerant universal quantum computer is available that can factorize very large numbers, encryption techniques are still secure. Okay, and so that's just to give you a perspective as to why there's this global race towards the development of quantum communication networks and different ultra secure encryption links. So to explain quantum communication, I'm going to do so in a very generic scheme, and I hope you don't mind. Some of you may have seen the scheme before, but you have your transmitter and your receiver, and the whole aim is that you need to encode your photons, your single particles of light, your quantum carriers, to either represent zeros or ones. And the way it's done is because it's a physical process, you can either encode using polarization of phase. And here I'm going to demonstrate the most easiest protocol, which is the BB84 protocol. So I'm going to use polarization as a means to demonstrate this. So in polarization, you have four states which you can encode. You can either encode into your horizontal, vertical, or your plus and minus diagonal or anti-diagonal and diagonal state. And so you randomly select these states to be encoded into your single photons that are transmitted to your receiver. Your receiver then has the ability to randomly select between two bases to perform a measurement. And once the receiver performs the measurement, you have first the key that was transmitted by your transmitter, and from the basis selection, a key that is produced by the receiver end. This entire process is done on a quantum channel. However, after this, you have to perform some post-processing in order to produce the secure key. And this post-processing is normally done on a classical channel. So on a classical channel, what will happen is Bob will tell Alice what basis was used during each measurement. And if Alice used the same measurement basis, they will keep that measurement. And if they use different bases, then they will discard this measurement. And through that process, they can produce a sifted key, which can undergo further post-processing in order to produce a secure key. Now, I want you to keep this in mind because when I talk about satellite-based quantum communication, I'm going to refer to how the sifted key is produced in our experiments. Okay, so if we look at the projection, and this was the prediction now that was made back in 2020 of where this field of quantum communication is heading. You already heard from Francesco when he mentioned that back in 2010 we had the first fiber-based quantum link in Durban. And so we know that these fiber-based QKD systems are now commercially available. So you can easily purchase a fiber-based QKD system. That is one area that has made many developments of late. However, there's still this progression towards the development of satellite-based quantum communication. And easy enough, they predicted in 2025 that we will have some satellite-based QKD experiments, and we now can count ourselves as a tick box that we have now in this race of saying we have implemented satellite-based QKD as well. But you can ask yourself, why is it that we need to develop this type of technology? There is this drive to develop what is known as a quantum internet. This will be a distributed quantum network that will be able to network quantum computers to quantum sensing devices and quantum communication. But the requirement for this would be satellite-based quantum communication, because without satellite-based quantum communication, it's going to be very difficult to produce a holistic quantum network, and hence the drive to develop these technologies. So before I dive into what was established, let's look at the challenges, because this is important. There is this two links that is used now to implement quantum communication. You have fiber links and free space links. So free space links include point-to-point ground communication as well as satellite-based links. Now, one of the challenges of fiber links is that they're limited in distance, because even with very ultra low fibers, we can only reach a distance of about 500 kilometers. And so that is really a limitation. The other limitation is the encoding. You can only encode in phase, because polarization is fibers are birefringent, and this also creates another factor that needs to be considered when you build these systems. In free space, you can exceed the distance. However, you have atmospheric turbulence to deal with, which then reduces the survival of the single photon, and this is also a problem. So if you have to look at transmitting or increasing the distance over point-to-point ground communication, there too you're limited, because of the atmospheric turbulence, which plays a very pivotal role in these systems, because they will actually diminish the signal. So in order to actually achieve these long distances, you have to move towards quantum satellite communication. We know for a long time there are two challenges in quantum communication: increasing the distance and increasing the key rate. So increasing the secure key and increasing the distance. And until we can't achieve those two constraints, then we cannot get to a quantum network. So to get to a quantum network, we really need to push that limit in increasing the distance of the quantum link as well as increasing the key rate. So that brings us to this drive towards the development of satellite-based quantum communication, because satellite allows us to increase the link distance. And the reason being is that there's only a 10-kilometer in which the single photons transmit through the atmosphere, and the rest is in space. And so that allows us to increase the distance even further. So a number of countries are pushing towards the development of satellite-based technology. You can see Singapore got the Spooky Q, USA got say CapSat, the UK got UK Quark, Canada's got KeySat, and then Australia and France is working on nanobobs. But the two satellites that has actually shown a lot of promise and actually resulted in real-time QKD demonstrations is the satellites launched by the Chinese collaborators. And this is the 2016 NITheCS satellite, as well as the satellite that we use, which is Jinan 1, that was launched back in 2022. Okay, so that comes down to the fact that if we look at NITheCS satellite, the NITheCS satellite was the first satellite that was launched by the Chinese collaborators at the University of Science and Technology. This was basically the first satellite that was actually deployed and showed real time that you can actually produce quantum satellite links. The satellite was launched into the lower Earth orbital, and it was a coverage of 500 kilometers. So it was launched 500 kilometers above Earth. The problem with the satellite was it weighed a lot. It weighed 600 kgs. So it's quite heavy. It has because it's in orbit, it has a limited time to perform experiments. So the time for the experiments are only 6 minutes, because the satellite is constantly in orbit. And you had to be in the shadow of the Earth to be able to perform any experiments. So that was the first satellite that was launched back in 2016 by the University of Science and Technology of China. However, they then realized that if they want to aim towards this quantum network and develop a quantum constellation, the satellite is too heavy. And they have to now look at ways in order to miniaturize the satellite in order to produce a quantum constellation. So they have shown numerous quantum links with the Messier satellite. Back in 2017, they showed that they could do a downlink, so sending single photons from the satellite down to a ground station. They have also shown the implementation of an uplink in 2017. But the most groundbreaking was also the fact that they could do entanglement-based QKD with this. However, what they also observe is that as you increase the distance of this quantum links, one of the challenges was that the secure key rate decreased. So you can see as they move from 645 kilometers to 1,200 kilometers, the key rate moved from 12 kilobits per second to 1 kilobits per second. This is a drastic decrease in the secure key rate. And this, I said from the start, is a major challenge. If you increase the distance, you're decreasing the key rate, but you need to increase both in order to get to a quantum network. The most promising experiment, and this was the first intercontinental link that was demonstrated, was the 7,600 kilometer link between Austria and China back in 2017 and then published in 2018. This was a key system that they actually were able to secure a Skype call between the two countries. And this was using the Messier satellite. And so back then in 2018, they then realized that, the Messier satellite verified that it is actually feasible to perform satellite-based quantum communication experiments. However, in order to scale up and produce a constellation, it would require a much smaller satellite than Messier's. It will also require a portable ground station in order to exchange keys between the satellite and the ground station. And so this was one of the challenges that they faced back then, even in 2018, is this realization that if we want to develop this quantum network, we need to make changes and adapt the system. So back in 2020, we started this collaboration with the University of Science and Technology of China. And our collaborator on the Chinese team was Professor Zhuan Yin, who was actually the chief designer of the quantum payload of the Messier satellite. So she designed the entire quantum payload for the Messier satellite. And the group leader is Professor Jay Pan, whom I mentioned before, who's leading the quantum technology in China and I think globally. And then it's myself and Francesco. Francesco needs no introduction. We know him as the director of NITheCS, but he is also the pioneer that brought quantum research to South Africa. And together with his postdoc, Abdul Rahim Mirza, they implemented the first fiber-based quantum link back in 2010. And so now we have the pleasure of introducing you to the first satellite link. And I think of Renee because Renee keeps telling me she's very impressed to see that the two lead scientists for the experiments on both teams are females, which is quite an achievement. And we're quite happy that we get the support of everyone to actually grow this research field. Okay, so let's get into the crux of what we implemented. As I mentioned, that the first satellite launched by the Chinese was the Messier satellite, but this was a satellite that was extremely heavy. It was 600 kgs, but to develop a quantum constellation, you need a much lighter satellite. And so they built Jinan 1. Jinan 1 is a microsatellite. It only weighs 100 kgs. And the quantum payload for the transmission of the single photons is only 35 kgs. For the Messier satellite, this quantum payload was approximately 250 kilograms. So you can see there's a drastic change in miniaturizing the system to make it feasible to develop a quantum constellation. One of the other changes that was made is the Messier satellite had to perform the quantum key distribution process across the quantum channel, and thereafter the post-processing took place at a latent time. And this latent time was 2 to 3 days because they use microwave technology, which is limited in their bandwidth in order to perform the post processing. In Jinan 1, we are actually performing real-time key distribution extraction because the microwave process was replaced by lasers. And so now you can use lasers to do real-time QKD. So you're not waiting 2 to 3 days to obtain your secure key. You're obtaining your secure key immediately while the experiment is live. And this is one of the biggest advantages. So if you want to go towards a quantum network, this would be required. You can't wait 2 to 3 days to produce a secure key. You need to produce a secure key in real time. And then so Jinan 1 was launched back in 2022. So just to give you an idea, I'm not going to go too much into the detail, but you can see that the satellite had a quantum payload. The payload compartment is denoted by that orange box. This is where the source for the single photons as well as all the lasers for the bidirectional communication is mounted. It then had a tracking system that was in front of that to basically synchronize with the ground station. And it actually had solar panels as well mounted to it. And so this is what the satellite would look like. Um, Let me see if this works. So that's, okay, I think it's removed. So that's what the satellite looks like. So it really is a microsatellite that's 100 kgs. The other improvement was that, working with a microsatellite, you also had to have a reduced ground station. So when they first implemented these experiments, they started off with fixed ground stations that weighed about 13 tons, so 13,000 kgs. And you can see the diameter, it's 4 meters by 3 meters, so it's quite a large telescope. But you can think about it, if you want to develop a quantum constellation, you need to also miniaturize your ground stations and you need it to be portable. And so the ground station we used for these experiments only weighed less than 100 kgs. So this is quite a drastic improvement as well, from 13,000 kgs to less than 100 kgs in weight. And the dimensions was much smaller as well. It was 1.2 by 0.5 meters. So the way this was achieved is that there was a Newtonian-based telescope. In the portable ground station, a Cartesian-based telescope was used. This allowed us to use two mirrors. The primary mirror was a concave mirror of a focal length of 280 millimeters, and the secondary mirror was only 5.1 millimeters, and this was a convex mirror. The advantage of this particular telescope is that it has folding optics, which means you can reduce the tube length, and the tube length was reduced to about 200 millimeters only. However, you can still increase the path length because of the folding optics. And so this allowed to produce a telescope with a shorter tube length but a longer focal length, and miniaturize it to a point where it's then a portable ground station. And so this is then the ground station on the roof of the engineering building at Stellenbosch University. You can see the beautiful mountains on the background. And this was implemented for almost 2 weeks on the roof to perform experiments here in Stellenbosch. So it's quite a small telescope as opposed to the large telescopes that we started off with. Okay, so as I mentioned that there was numerous institutions involved in this project. And so there was links at numerous universities and institutions in China. And then the one link in the Southern Hemisphere was us in Stellenbosch. And so you can see that there are a number of ground stations that was mounted at these various links. You can see Beijing. They also mounted it on a ship once, so it really is that portable. And we were able to perform these experiments using the satellite Jinan 1, which is that micro satellite. So just to give you an idea of how Jinan 1 works as opposed to NITheCS, as I said, one of the advantages of this satellite is it allows for bidirectional real-time QKD, which means that it actually has two lasers on the satellite, and the ground station also had a laser in order to do the bidirectional communication. So let's start from the satellite itself. So Jinan 1 has a 850 nanometer satellite, and this is for doing quantum communication. The system worked on a decoy state QKD process. Decoy state means that there was three signals, or the signal, a vacuum state, and a decoy state that was produced. This was produced using this 850 nanometer laser in using a lithium niobate crystal in a Segnac interferometer. And you can see that Segnac interferometer is the ring-shaped interferometer here. That allowed you to produce the decoy state, the signal, as well as the vacuum state. And the reason why you need a decoy state, the decoy state allows you to trace whether there's an eavesdropper in the system. Because for every transmission of a single photo of a signal, you would know what the decoy state intensity was. And if an eavesdropper is in the system and that changes, that leaves traces in the system which is detectable. So the decoy state was there to basically vary the intensity to detect if there's traces of any eavesdropping. Then you had your signal state and your vacuum state that was created using this lithium niobate crystal and the Segnac interferometer in an 850 nanometer laser. Okay, so this was the signals that were sent down to the ground station. Thereafter, the ground station had a laser as well at 1538 nanometers. So now you've started off where you've produced the photons, they encoded. You're sending this down to a ground station where it's going to be measured. Okay? Once these photons are measured, what happens is the measured state as well as the basis that was randomly selected is sent via a signal using that 1538 nanometer laser back to the satellite. Okay? So it's sending that information of the measurement detection process back. At the satellite will do vector basis comparison because obviously it's known at the satellite what basis was used to prepare the states. And that is then sent back to the ground station using the 812 nanometer laser. Okay. Once it reaches the ground station again, then the secure key is created based on that analysis of the basis reconciliation. Okay, and so that's how the bidirectional QKD worked in real time. So you didn't have to wait 2 to 3 days to do post-processing. It's just the transmission of the lasers back and forth that allowed you to produce the secure key. So here's us setting up on the roof of the engineering building. That's just the satellite and the control box, which allowed us to track the satellite as well as obtain the secure keys. And I should thank Professor Willem Jordan as well as Professor Arno Bernard, who are the two engineers in the engineering department that gave us access to the roof as well as helped with the logistics on the roof to allow us to implement this system. So you can see that the sun is setting behind the satellite. So now this satellite, behind the ground station, there's a reason why that satellite is placed and positioned specifically there. The satellite is launched into sun synchronous orbit, which means the satellite passes north to south or south to north. So the ground station had to be positioned so it can track south to north, north to south, because it doesn't want to be tracking east and west. Okay, so the satellite is launched into the sun synchronous orbit. Now, before we could perform these experiments, we wanted to ensure that the satellite, the ground station, can actually track a moving object. So the night before we could start our experiments, we decided that was the night that the International Space Station was going to be visible in Stellenbosch. And so we decided on this night we were going to first and foremost track the International Space Station to see whether we could track a moving object. And you can see this was the bottom end is the image from the ground station. So it looks a little bit grainy. You can see the silhouette. The reason for that is that was the night where the humidity was a little bit high. And so there was water droplets that was collecting on the ground station, which resulted in this hazy image. Normally the image is much better, but you can see the silhouette of the ground station there. And so what we were able to do, and I hope you can see it, I'm not sure, but you can see it. So there's the International Space Station moving over Stellenbosch. Okay, so you can see the video of this International Space Station moving. And so we were able to track the International Space Station as it moved across Stellenbosch in order to see that first and foremost we can track a moving object. First test before we actually try to test Jinan 1. Okay, so that was the night before. Then it was the 13th of October when we wanted to start these experiments. But of course, the satellite only passes at two times during the day and during the night. And so there was very specific times in which we could perform this experiment. Okay, so most of the time the experiments could only be performed really early in the morning, like just after midnight or just before midnight. So there was this window period in which the experiments could be performed, but they could only be implemented for 6 minutes. So every night at 10:30, we would go to the roof. We'll set up the experiment. It normally takes half an hour to track. So the way we would set it up is we would track a known star, and we'll make sure that the ground station can track that known star. We'll make sure that it's set up and aligned, and then we wait until the anointed time when the satellite is going to pass us for that 6 minutes. What is important to note is the satellite starts off at 10 degrees off the horizon, but it gets to an elevation angle. Now, if that elevation angle is high enough, the signal is stronger. And so on days when the elevation angle was higher, we would get better signals and better secure keys. So we would perform this experiment, and you can see the start time when the satellite starts. We can start tracking, and then the end time as well as the mid time when the satellite is at that highest elevation angle. And this we could then look at different days in which we could perform this experiment. Okay, so most of the time it was very much close to midnight or just after midnight. And then, of course, we ignore any times when the satellite passed in the day, which we can't implement experiments during the day. Okay, so the 13th of October was the day when, or the night when the first experiment went live. So this is the day when we first got the first secure key rate here at Stellenbosch University. And I'm going to try and play this, but I'm going to see if it works. So I had to, the zooming, it's very bad quality because I had to really zoom into this video. But you can see Jinan 1 that's passing over the atmosphere. And you can see the green light from Jinan 1. That's one of the lasers being transmitted down. And so that is the satellite. So it is a little bit jumpy, but that's because I had to zoom into this to kind of create a way for you to see this Jinan 1. So you could see it visibly. On very clear nights, you could see the satellite passing. And you would see the green laser from the satellite. So you would be able to notice that is the satellite that's passing over the atmosphere. So on the 13th of October, we made history here in Stellenbosch because that was the first quantum satellite link that we did implement. So that marks history. I'll come down back to the actual results soon. Our Chinese collaborators joined us in South Africa during the time of the experiments as well. And so you can see that there's some of them in the photo here. We would first photo on the top is find a star that we want to align this ground station to. So we would use a very strong laser beam to point to a star that we want to align it to. We'd align to that star and then wait almost an hour before the satellite passes. And this is some of the members. So you can see Prof. Zhuan Yin in the cream coat. She's the lead scientist in our collaboration on the Chinese team, and then fellow colleagues as well. Okay, so now I'll come back to the actual results. So what did we obtain? Okay, so I'm going to start off with the bottom corner because bottom end because that's our results. So we implemented over 5 nights where we really got good keys. The first night of the 13th of October, the weather wasn't the best. I think it was one of the nights where we had very high humidity. And so, and then also the elevation angle was not the best on that night. It was below 40 degrees. And so the first time we implemented, we only had 315,904 bits. Because there was a time twice on the 13th of October, we were able to implement twice, and we saw that that almost doubled. And that's because the humidity dropped later on when we implemented that. The elevation angle is still below 40 degrees. The 15th of October, we also got similar results to the 13th, but then we started seeing a further increase. And what we at this time on the 15th of October told ourselves, we need to aim for a million secure, million bits of our secure key. And so what we were doing is keep on checking the weather, checking the elevation angle to see which is the day where we think we're going to get the best results. And the day we got the 21st of October, it was when the elevation angle was 57 degrees. So it was when the elevation angle goes up that we can improve our secure key. And so this moment I must speak about before I actually go back to the results. So this moment was really the moment that we really jumped for joy. I remember Helen and I on the 21st of October, while performing this experiment, we was hoping that this was the night where we knew the elevation angle was the best. So we like were hoping that we can get to this 1 million bits. We sat at that laptop and stared at the screen the entire time of the duration of the 6-minute path, hoping this key rate goes above a million. And I remember the moment we got it, it was 12:23 a.m. in the morning. I sent a message on the group chat and I was hoping Francesco was awake to see it, but then he saw it at 9 o'clock, I think, in the morning. But this was like the best night when we were really hoping we'll get to a million bits. And we did. Now, why is this so important? Well, they implemented this link at various positions as well in China. So they implemented it in urban areas in Jinan as well as Beijing. And the most they could get in an urban area was 5,700 odd bits. So nothing close to our million bits. And then even in their mountainous areas, they went up to 578,000 bits. But because of the ideal weather conditions in Stellenbosch and our clear skies in South Africa, we were able to get such a high secure key. They themselves were so impressed. I think after we obtained this result, the WeChat groups went crazy. No one slept that night because they kept saying, you know, the results are the best results we've ever obtained with Jinan 1. So yeah, low humidity, clear skies is what is required in order to ensure that you can really push the limits with the secure bits. So as I said, the satellite was launched in July of 2022. So since then, they've done numerous satellite links. Our link was only implemented last year in 2024, but you can see that the links had various elevation angles and various final secure keys. The highest, as I said, was the 578,000. That's the 12th of July 2023 in the Chinese side, which was the mountainous areas. And then the highest for us was in October 20th or 21st, I think, when we got that million bit secure key. Okay, so that was quite an amazing achievement here in Stellenbosch. Okay, so now that we got our secure key, so what? What do? We have to show proof of principle that we can actually encrypt messages. And so what we did is we used the secure key from the Beijing ground station together with modulus of a one-time pad. So this is random bits of numbers. And they encrypted image and they sent to South Africa. We took our secure key of our 1 million bits from our ground station, did the same, and encrypted a message to China. And so they sent the Great Wall of China to us, and we sent the site of the experiment from Stellenbosch to them. So this was quite an achievement because we were able to encrypt an image and send it across between China and South Africa across this distance of 12,900 kilometers using also the secure keys from our ground station. Now, I should put into just mention for those that may not know, one of the challenges of one-time pads, although it's theoretically secure, one of the challenges is that the key has to be as long as the message. And once you use a one-time pad, you have to discard it. So you can't use it numerous times. And so one of the challenges of a one-time pad is the key distribution process. But quantum communication actually provides that solution. It provides a way to perform the key distribution. Okay, so that actually enhances security. So just to bring it back, complete cycle, we implemented the first quantum satellite link in the Southern Hemisphere. This is now the longest intercontinental link between the Northern and Southern Hemisphere of 12,900 kilometers. And we were very proud that we got the highest secure key with Jinan 1 here in Stellenbosch. So quite a proud moment for us. Just to give you an idea as to why we obtained such good results, is that, when you're looking at these two satellites that the Chinese collaborators at University of Science and Technology of China has launched, the NITheCS satellite and Jinan 1, one of the biggest challenges they had with NITheCS was the weight of the satellite as well as the weight of the payload. And you can see that this was significantly decreased with Jinan 1. One of the other challenges they had was the ground stations that they were using NITheCS was quite heavy, 13,000 ton as opposed to less than 100 kgs. The other challenge was the communication for the key distillation, 2 to 3 days as opposed to real time. So this is drastic changes in the way the system Jinan 1 was set up. More so, Jinan 1 allowed for 2 to 3 times faster key generation, which also helped in increasing that secure key. So I have to also talk about some of the limitations, because we can't leave an audience thinking it's all perfect. There are limitations, and we should actually touch on them. Some of the limitations with all quantum satellites that are launched thus far is that they all launched into the lower Earth orbiter, which means they're constantly orbiting. This means that you have a limitation in the time which you can perform experiments to only 6 minutes. Now, in order for you to develop a quantum network, you need to increase the time frame in which you can perform experiments. And so in order to achieve that, you have to get to geostationary Earth orbiter, where the satellite is fixed and allows you to increase the time frame in which you can perform these experiments. So no more an orbiting, but a fixed satellite. Furthermore, what was really an achievement of this Nature paper and these results is that because of the miniaturization of the satellite and the ground station and the proof or principle that it is possible to increase the distances to 12,900 kilometers, this means that this paves the way forward towards this quantum constellation. This means that we can aim to achieve this global scale quantum network using microsatellites that are launched into the lower Earth orbital or even into the geostationary Earth orbital, as well as these portable ground stations in order to connect various sites to produce a quantum constellation. So this paper really answers this practical challenge of producing a quantum network. So I hope I've given you an overview of the quantum satellite link. We are quite proud. If you get a chance, do read the paper. It's quite a nice achievement, and we hope that in a few years' time, we'll be hearing about more developments in this field, and maybe, who knows, we might have a quantum constellation by then. But this is quite an achievement for us in South Africa, so hopefully we can enjoy this moment and enjoy the fact that we are also part of this global race to demonstrate quantum satellite links. Thank you, Francesca.
Yaseera, thank you so much for the excellent talk. I'm sure people have questions for Yaseera here and in the online audience. So who would like to go first? A Chinese guy. Yingshe, please.
So first, I really want to congratulate you hugely on this achievement. And I think this is a very interesting and very smart collaboration that because if we launch our own quantum satellite, that the country will need to dump a lot of resources on this. But you just very smartly piggyback this on the existing one and to make this global network. That's just phenomenal. I mean, I think that whole thing is phenomenal. And spend less money and do more work. That's absolutely phenomenal. And I think my question is, what is your? I mean, suppose this quantum global network it can be established and so on. What is the information that you want to process? What is the practical use of this whole network?
It's going to be to ensure security, right? So if we look at our current encryption techniques, quantum communication is basically going to be underlying principles of security below the current encryption techniques that will allow you to enhance current encryption. So you can think of it being applied to all your 5G and eventually 6G networks to ensure security, ensure password protection, so medical data, anything that needs to be secure. This technique eventually, when we have this global quantum constellation network, will be able to protect.
Any other questions, please?
Hi, Yaseera, thank you very much. Very interesting, and congratulations. I just have the typical stupid question about, you were sending some parts by the single photons, but you were also communicating some parts by a classical channel. And I would love to understand, so you have if you say that you send the pictures, did you really send all the data of the pictures over the single photon channel, or did you only send the key to decipher them over the photon channel? I would like to understand that.
So yes, the actual quantum channel is only to produce the secure key. Yeah, just to give it a shot.
Any other question? Please, at the back and then front.
Thank you very much. So I just want to understand one thing. Like when you are deciding to set this the ground station, like do you just choose a place randomly, or you just choose a specific places depending on like maybe geographically? And like if you are looking it was clear like the data from Stellenbosch we got was very impressive compared to the one in China. Is it just because of weather, or has it also to do with the geographical location?
No, most of it is weather. So also remember, if you are implementing in an urban area, you've got industry around, so you've got pollution. Pollution is going to affect the secure key. Then you also got weather conditions, which plays a vital role. So if you got high humidity, if you got overcast weather conditions, you really can't implement these links. So it's very much weather dependent. It's also very much also dependent on where in the city you place it. So one of the advantages we had with placing it on the roof of the engineering department, it was away from the Stellenbosch Central, which means less light pollution. So when the satellite was passing over the ground station, it was actually in an area where there was not, it was more closer towards mountainous areas. So it was much less light pollution than you would expect if I had to put it here on the roof of the NITheCS, where you have constant light pollution all around you. So there are many factors that you have to consider when you place in the ground station. Ideally, you want low light, low pollution, away from industry. Unfortunately, you can't control the humidity, but you can control when you perform the experiments, when it is low humidity, and you want clear skies. So I remember there were days when we would just be tracking the weather constantly, and I'll come to Francesco's office like, what's the weather today? You know, my app says this, what does your app say? Because we're constantly tracking the weather to see, you know, is it going to be ideal conditions, because the elevation angle is ideal, but is the weather conditions going to be ideal to implement or not? So, you know, there's a number of factors that goes into the determination whether you're going to get a very good secure key or not.
Hi, firstly, your work is really incredible, so thank you for this presentation. My question is, when you talk of a quantum constellation, what does that look like in terms of how many additional satellites are we adding into the Earth's orbit?
Well, that's several hundred, maybe. Yeah, so they approximate, but I'm not 100% sure. They approximate about 100 satellites that will probably have to be launched, microsatellites, in order to produce this quantum constellation. So yeah, I know that's a lot of space junk eventually, because what I should mention is that NITheCS satellite is now decommissioned because it was a 5-year period in which any quantum satellite experiments could be performed, and they decommissioned it, and then they launched Jinan 1. So now to actually implement a quantum constellation, you'll have to launch at least 100 satellites. which obviously will become decommissioned again, right? So yeah, that's kind of one of the problems as well.
Yes, congratulations again and with your co-authors.
Yes.
I just have one quick question. We are in an era of climate change. Is this going to be affected or still stands?
Oh, that's a hard one. Can I choose not to answer? No, I mean, you know what? Yeah, we are in a problem of climate change. Eventually, you know, if we look at how our seasons occur, it's always pushed back a month, pushed forward a month, and we can't really predict weather sometimes correctly. So these experiments, unfortunately, have only to be performed during ideal weather conditions. We have that advantage here in the Western Cape that, you know, most of the year besides winter, we have ideal weather conditions to implement. But you are right, weather conditions with climate change is going to be playing a vital role in these developments going forward. But the quantum constellation will help, because if you have a number of ground stations at various positions, and if one area has bad weather, another area has better weather, you could produce your secure keys in an area where the weather is more promising, as opposed to an area where, you know, you're not going to get a secure key at all.
And they're mobile, so you can
Yeah.
just put them in your bucky and move to where it stopped raining.
Put them on the ship too. So-
I think my question is that is about this weather thing which you mentioned. Is this specifically related to the 2 point Beijing and Stellenbosch, or this is also kind of related to the transmitting atmosphere of global climate, which the later case would be related to the global climate change, right?
It's the second, so it's the latter. So it's the transmission. Because if you look at it, the reason why point-to-point ground communication, only the furthest they implemented to date is 144 kilometers between La Palma and Tenerife, is that the turbulence plays a vital role in those links. And as long as you go horizontal, you're going to always deal with atmospheric turbulence. If you go to a satellite, you're only dealing with atmospheric turbulence for 10 kilometers. After that, you've got vacuum, right? So you've got space. But if the weather is still not ideal in that 10 kilometers, that is also going to reduce the secure key. And we've seen it. When we implemented on the 13th of October, the key rate was quite low in comparison to the 20th of October, where we hit that million bits. So it is really weather condition, and it is for the transmission of that quantum channel. It's the quantum channel that's the problem when it comes to the climate.
I'm just hypothetically say if you are still in Durban, then Durban humidity is higher than Stellenbosch, then that may be a problem.
It's been a big problem. So if we had to implement it somewhere else, like a city like Durban, I don't think we would have gotten to 1 million key rates, because I think it would have been also similar to the weather that they had in China when they did implementation. So it was because of the ideal conditions here that we got such high secure key. So
I join everybody with congratulations for this spectacular news, and thank you so much for sharing with us. I have two questions. The second one is more a joke than a question. The first one is, you told us about those number of bytes that you receive. How does it affect in terms of getting the key? The different numbers.
okay, so this is so let's just go back here. So you're talking about this.
Yes.
So this is actually the secure key. This is how many bits are in the secure key.
Okay.
So this is the actual secure key, because
Each of them are
real time. What we are interested in is just the final key. So if we go back 1 second, I think I could provide you better information. Yeah. So here you can see that you also get the sifted key, R sifted, and thereafter, based on what your sifted key quantum bit error rate is performed. So what happens is when the transmission takes place, 10% of the bits are used to perform the quantum bit error rate. 90% is then used to perform further post-processing to get out the secure key. So that will then undergo the sifting process, etc., to come out to the secure key. So you can see that we started off with quite a large number of raw keys. even on the 20th of October, and we only ended up with 1 million bits in the end as a secure key. So yeah, that would be the final key.
And the second question is, so since you kept this work secret, your visitors from China, was their visit also kept secret, or?
Okay, so they actually came in, and I think we had a conference at that time. So we were hosting the International Commission for
That's
Optics
clever.
conference. And they, Professor Zhang was one of the plenary speakers at the conference. And that was the same time that she was here in South Africa, so we could implement the experiment at the same time. And it was quite a nice achievement to have them here in South Africa.
Thank you.
Do you have any questions from the online audience? Donovan knows. Yeah.
Question.
Please. Okay. We can go back to you just now.
Okay, we have one. Okay, if I understand correctly, the experiment uses laser light, which consists of millions of photons. I thought one needs single photons to do QKD. To what extent is this experiment quantum?
So the photons was actually a pulsed laser that allowed you to produce a decoy state protocol, which means you're using weak coherent pulses of a signal, a vacuum state, and a decoy state. So it wasn't billions of photons.
Menika, you had a question. No. Yeah. Then, Yaseera, then thank you so much again for the very nice talk. Thank you very much. And thank you to the audience here and the audience online. And according to plan, there should be some snacks and drinks outside. Yeah. So thank you very much.